Hello, welcome to 2.5, Implicit Differentiation. So, the explicit form of an equation is an equation in the form y equals 2x cubed plus 5 or y equals 1 over x. That's an explicit form. It's solved for y equals something. So an example of an equation in implicit form would be x times y equals 1. That's the implicit form, whereas the explicit form would be y equals 1 over x, where we solve for y. So the implicit form of an equation is whenever the y would not be isolated, or one of the variables is not isolated. So we can differentiate an implicit equation using implicit differentiation. Now this really uses the chain rule. So assuming y is a function of x, we can use the chain rule with this. And we differentiate with respect to x. For example, the derivative with respect to x of x squared equals 2x. We're good with that. The derivative with respect to x of y squared, knowing that y is a function of x, that's x here, it's going to be 2y times dy dx. So the derivative of y with respect to x. So you get the derivative of the outside function is 2y. Then times the derivative of what's inside. If we know that we have the inside function where y is a function of x, and that's what this part is. That's using the chain rule. So the derivative with respect to x of x squared plus y squared would be 2x for the derivative of x squared. Then 2y dy dx for the derivative of the y squared. So the way this works is whenever you have a function where y is a function of x, you'll always have this dy dx as some value, but we don't know what it is. And we're trying to find that value. So guidelines for implicit differentiation. Differentiate both sides of the equation with respect to x. Collect all the terms involving a dy dx on one side, typically the left side. Move all the other terms to the right side. Factor out your dy dx and then divide both sides by whatever the factor is there times the dy dx. So you're going to divide that out. So you have a dy dx equals in the end. So our first example here, our second example, the first one was typed up. This example, find dy dx given that x cubed minus xy plus y squared equals 4. So we're going to take the derivative with respect to x of x cubed minus the derivative with respect to x of xy. That is a product, so we're going to have to use the product rule here, plus the derivative with respect to x of y squared equals the derivative with respect to x of 4. So this is 3x squared minus, now we've got a product rule, we'll do the derivative with respect to x of x times y plus x times the derivative with respect to x of y plus then the derivative with respect to x of y squared would be 2y dy dx equals, and the derivative with respect to x of 4 is just 0. So it's 3x squared minus d dx of x is just going to be 1 times y, carry the minus through, minus x dy dx plus 2y dy dx equals 0. Now these terms have a dy dx. They're going to stay here on the left side. I'll move the 3x squared. I'll move the y, the negative y. And we have negative x dy dx plus 2y dy dx equals, I'll do y minus 3x squared. So we can factor out the dy dx here, and we have 2y minus x equals y minus 3x squared. So our dy dx would be equal to y minus 3x squared divided by this factor. It would be 2y minus x. Okay? So I divide both sides by the 2y minus x, got the dy dx by itself. But notice the answer has both y's and x's in it. That's going to happen. Example 3, if possible, represent y as a differentiable function of x. So if we added y squared to both sides, we'd have x squared equals y squared. So then y squared equals x squared. To solve this, we take the square root of y squared, it's plus or minus the square root of x squared. So y would equal plus or minus x. And the next one, we have x squared minus y squared is 1. So I will subtract the x squared from both sides. So negative y squared equals 1 minus x squared. If I divide both sides by negative 1, y squared equals x squared minus 1. And then if I take the square root of y squared, it would be equal to plus or minus the square root of x squared minus 1. So y equals plus or minus the square root of x squared minus 1. And this would be for x being greater than or equal to 1, because if it's less than 1, you're going to have something less than 0 in here. X being less than or equal to negative 1 for our domain. I have one more of those. X minus y squared equals 1, so I'll subtract the x from both sides. Negative y squared equals negative x plus 1 divided by negative 1. Y squared equals x minus 1. So y squared equals x minus 1. I'll take the square root of y squared. So y equals plus or minus the square root of x minus 1. And again, this is for x being greater than or equal to 1. Okay, example 4 says, find dy dx by implicit differentiation and evaluate the derivative at the indicated point. X plus y cubed equals x cubed plus y cubed is our equation at negative 1, 1. So this is the same as finding the slope of the tangent line to the graph at the given point. So derivative is still going to give us the slope. We get the slope, get a point, doing the same thing as we'd normally be doing. This time, though, we're actually going to have an x and a y in it. So I'm going to scroll this up so we have more board space to work. So we have x plus y cubed. We're going to take d dx of that equals d dx of x cubed plus d dx of y cubed. So this derivative, we've got the chain rule. We have 3 times x plus y squared times the derivative of what's inside. The derivative with respect to x of x is 1. The derivative with respect to x of y is dy dx. So this derivative is the 1. This derivative is dy dx. Equals, this becomes 3x squared, the derivative with respect to x of x cubed, plus the derivative with respect to x of y cubed becomes 3y squared dy dx. So I'm going to have to distribute here. We have 3 times x plus y squared times 1 plus 3 times x plus y squared dy dx equals 3x squared plus 3y squared dy dx. So if I want my dy dx terms on the left side, I'll subtract 3y squared dy dx and then subtract 3 times the quantity x plus y squared. So we have 3 times the quantity x plus y squared dy dx minus 3y squared dy dx equals 3x squared minus 3 times the quantity x plus y squared. Now, one thing we could do is divide all the 3's out. And then if we expand, well, let me factor out a dy dx here. dy dx times the quantity x plus y squared minus y squared equals x squared minus x plus y squared. And then we could just divide this through x plus y squared minus y squared. So this part divides out. And we have dy dx equals x squared minus x plus y squared over x plus y squared minus y squared. And if you really like to play with the algebra, we could expand these two parts here. We have dy dx, that's x squared minus 2xy minus y squared over x squared plus 2xy plus y squared minus y squared. That cleans it up, I guess, a little bit. And the dy dx is negative 2xy minus y squared over x squared plus 2xy. And then we're going to evaluate it at 1, 1. So dy dx at negative 1, 1 is going to be negative 2 times negative 1 times 1 minus 1 squared over negative 1 squared plus 2 times negative 1 times 1. That's going to be 2 minus 1 over, that's 1 plus negative 2. That's going to be 1 over negative 1, which is negative 1. Okay. Now, I did not have to do this step here. I chose to do this step to expand it and make it a little simpler. You could have just gone with that. We go on to the next page. Determine the slope of the graph of 3x squared plus y squared squared equals 100xy at the point 3, 1. So we're going to take the derivative with respect to x of 3 times x squared plus y squared squared equals ddx of 100xy. So we have a product, or first a chain rule, not a product rule here. So that's 3 times 2 times x squared plus y squared to the 1 power times the derivative of what's inside, 2x plus 2y dy dx equals this derivative. We've got a product rule here, 100 times 1 times y plus 100 times x times dy dx. So really, I hope you see the pattern here. Is you can treat, taking the derivative of y squared, it becomes 2y dy dx. So you just treat the y like you would in x, except then after you do the derivative of the y part, you do a dy dx. Okay, I've got to distribute here, so it's going to be 6x squared from right here times 2x plus 6x squared times 2y dy dx plus 6y squared times 2x plus 6y squared times 2y dy dx plus 100y plus 100x dy dx. Woo! Getting kind of involved. So this is 12x cubed plus 12x squared y dy dx plus 12xy squared plus 12y cubed dy dx equals, then we have 100y plus 100x dy dx. Okay, so this term here and this term here are going to go away, and this is going to move over. So we're going to do a minus 12x cubed, and then a minus 12xy squared, and then a minus 100x dy dx. And it'll give us all the dy dx's on the left side. So we'd have 12x squared y dy dx plus 12y cubed dy dx equals 100y minus 12x cubed minus 12xy squared. So we'd have dy dx times 12x squared y plus 12y cubed equals 100y minus 12x cubed minus 12xy squared. So it's dy dx is going to be equal to this expression divided by this expression. 100y minus 12x cubed minus 12xy squared over 12x squared y plus 12y cubed. Oh, I forgot my 100 minus 100. Forgot all about that. Minus 100 x. And that should be in here too. Minus 100 x dy dx equals, there we go. Kind of squished in there. And there we go. We can leave it like that. We can divide out a 4 if we want to. Don't have to. So now we're going to plug in the point 3, 1. So our dy dx is going to be 100 times 1 minus 12 times 3 cubed minus 12 times 3 times 1 cubed over 12 times 3 squared times 1 plus 12 times 1 cubed. You're going to end up with, drum roll please, 13 over 9. I'm going to go on to example 6 now. Says find dy dx implicitly and find the largest interval of the form negative a less than y less than a or 0 less than y less than a such that y is a differentiable function of x. Then express dy dx as a function of x. So what we have is tangent of y equals x. So we're going to take the derivative with respect to x of tangent of y equals the derivative with respect to x of x. This derivative is secant squared y dy dx equals 1. Then we'll divide both sides by secant squared y dy dx equals 1 over secant squared y. So dy dx would be, we all know this from our pre-calc days, cosine squared y. Now, where is this going to be defined? From where to where? Well, from y is less than or equal to negative pi over 2 to pi over 2. I think it's strictly less than, because going back to the tangent part, it's undefined. And for the secant, so there. Now, since secant squared of y is equal to 1 plus tangent squared of y, this is an identity, we know this identity, and tangent of y equals x, secant squared of y would be 1 plus x squared. Also, knowing that dy dx is 1 over secant squared y, we could say dy dx is 1 over 1 plus x squared. Okay, so using that relationship. So we have here, or you can have that relationship with that value as well. Okay, we're going to go into our last page for 2.5. It says find the second derivative of y with respect to x. Oh boy, this is going to be an interesting problem. We have is a circle, x squared plus y squared is 36. So we'll first do the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 36. That means 2x plus 2y equals 0. Now we'll take the second derivative, the derivative with respect to x. Well, I guess we could take this a step further. If we subtract 2x from both sides, 2y equals negative 2x. So y equals negative x. Oh, I made a mistake. No one called me on it. I'm calling myself on it. You may have seen this. You may have been screaming, "No, Jeff, you forgot your dy dx with the y. You just said it was a rule." You're right. I said that was a rule. My mistake. Now, if I subtract the 2x from both sides, 2y dy dx equals negative 2x, and then we can divide by 2y. So dy dx equals negative x over y. There we go. Now we're happier. If we want to take the second derivative with respect of x with respect to y, no, of y with respect to x, this would be d dx of negative x over y. And we have a quotient rule. So our second derivative of y with respect to x is going to be low d high, so y times d dx of negative x, minus high, which is negative x, d low, which is d dx of y, all over the square of what's below. So our second derivative of y with respect to x is going to be y times negative 1 plus x dy dx over y squared. So our second derivative of y with respect to x is going to be negative y plus x times, what was our dy dx? Our dy dx is negative x over y. So I'm substituting negative x over y in place of that. So negative y plus negative x squared over y squared. We have a complex fraction. If I multiply on top and bottom by y over 1, that'll get rid of that. And our second derivative of y with respect to x is going to be negative y squared plus negative x squared over y cubed. Now, We could leave it like that if we'd like. Notice though that we have x squared plus y squared is 36. That means that x squared will be equal to 36 minus y squared. If I took this and put it in place of the x squared, putting this in here, negative y squared minus 36 minus y squared over y cubed. So it's negative y squared minus 36 plus y squared over y cubed. These go away. And what do we have left? Negative 36 over y cubed. So that's one way we can finish it off. Let's find it in terms of x. Let's find it in terms of y. Now if we take our second derivative of y with respect to x equals this part, negative y squared minus x squared over y cubed. And coming back to here, y squared equals 36 minus x squared. If we take this part and put it in place of the y's, we would have, not sure what we're going to be able to see here on this from the camera. Putting this in place of the y squared, it's going to be 36 minus x squared minus the x squared. This is negative though. Over, and that's y squared equals this. So y cubed would be 36 minus x squared to the 3/2. So our second derivative of y with respect to x in this case would be negative 36 plus x squared minus x squared over 36 minus x squared to the 3/2. The x squareds go away. And got that one circled. So our second derivative of y with respect to x is going to be negative 36 over 36 minus x squared to the 3/2. There's the other solution. So I also want to circle this one. So here it is in general with the x and the y, with only y's in there, with only x's in there. Okay, and with that, feel free to pause if you'd like. I'm going to go on to example 8. Find the equation of the tangent line to the circle at the indicated point. This one will not be nearly as bad as what we just did. So we want the derivative with respect to x of x squared plus the derivative with respect to x of y squared equals the derivative with respect to x of 9. It's 2x plus 2y dy dx equals 0. So subtracting 2x, 2y dy dx equals negative 2x, and dividing by 2y, so y, dy dx equals negative x over y. So our dy dx is going to be the negative of 2 over the square root of 5, or negative 2 root 5 over 5. So there's our slope. So y minus y1 equals m times x minus x1. So y minus root 5 equals negative 2 root 5 over 5 times x minus 2. So y minus square root of 5 is going to be negative 2 root 5 over 5x plus 4 root 5 over 5. And if I add the square root of 5 to both sides, y equals negative 2 root 5 over 5 times x plus, this is 4/5, this is 5/5 of this. That becomes 9/5 square root of 5. And that's the end of that problem. Okay. Well, I hope you enjoyed this section. I know implicit differentiation can be a little bit challenging. It can be a little intimidating. A lot of big words and a lot of processes. But we are growing in our mathematical abilities, and so I think you can all do this. Take a look at the homework, send me your questions, and I'll see you guys online. Thank you.